Hi, algebra students. There's no one in the classroom with me today just because of the ASVAB test happening here at West. I actually see some of you right now through my window taking the test out there. I wish you the best of luck if you are one of our students taking it. But at the end of the day, please don't stress about it. It's just a test where if you do well, it helps you graduate. But if you don't do well, it doesn't hurt at all. But I do wish you the best of luck. But because there's no one else in the room today, I'm talking directly to you people at home. The lesson that we're looking at today is going to be on how you graph systems to find solutions. One of the things we talked about yesterday is what a system is. Do you remember? A system, we said, is when you've got two or more equations. So one of the things we were doing yesterday was checking solution points for systems. We talked a little bit about what a system is. Today starts us actually solving systems of equations. There's going to be 3 different ways we learn how to solve systems. We are looking at the first way today, which is solving a system by graphing. Before we get into some of the problems, I want to quickly review what we said yesterday a solution point was. What do you remember about solution points? Our definition to solution points had 2 parts. The part we were using a lot yesterday is this idea that a solution point satisfies the equation, or if it's a system of inequalities, it would satisfy the inequality. Yesterday, we were checking to see if a point was a solution point. And for many of those problems, the way we did it was by using this part of the definition. We substituted in the point to see if it gave you something true, like 4 equals 4, or if it was an inequality, something true like 4 is greater than 3. The second part to that definition we learned yesterday, though, is that it is a point for a system of equations, or just a single equation. It's a point that lies on the line. So one of the things we had talked about yesterday is when you've got a single equation, a single line, there are a ton of solution points because there are a ton of points that lie on a single line. The math word we used yesterday was there are infinitely many solution points. But if you have a system of equations is 2 equations, that's 2 lines. One of the things our student in the room yesterday noticed is that for a system, there's only 1 solution point because there's only 1 point that lies on both lines. This is the part we're going to be using today when we talk about solving systems. All we were doing yesterday was checking to see if a point was a solution point. So I would give you a point and you would say, yes, that is a solution point, or no, it's not. Today starts us actually finding what that point is. The questions today are going to look something like this. I'm going to give you a system of equations. Remember, a system is 2 equations or more, but the problems today will just have 2 equations. So I'll give you a system, something like this, but now I'm going to be asking you solve the system. When I say solve the system, I just mean find what the solution point is. In order to do that, we can use that second part of the definition we just looked at, and the part that says a solution point is a point that lies on the line. To be a solution point for a system, it has to lie on both lines. What do you think we're going to do in order to solve this system? Well, if I know the solution point is the point that lies on both of these lines, I could use this graph over here, could graph both of these lines on the same graph, and find where those lines intersect. That intersection point will be our solution point. So in order to graph both of these lines, we're going to have to use some of the stuff we learned back in Algebra 1A. If I want to graph the equation y equals 2x minus 1, what am I going to do? Well, I want to start at our y-intercept. That is that -1. So I'll come down here, put a point at -1 on my y-axis. And then my slope is 2. If you're thinking rise over run, that means my slope is 2 over 1. I'm going to rise 2, run 1. So starting here, rise 2, run 1, rise 2, run 1. If you have paper in front of you that you are doing this on, It is especially helpful for today's lessons to put lots of points on your graph. I'm going to also go backwards by doing the opposite. Instead of up 2 over 1, I'm going to go down 2 backwards 1. And the reason I'm putting so many points is going to make sense in just a moment. So I've got all of those points. That is for this first line here. So I can go ahead and draw a line through all of those points. For my second equation, I'm going to do it in a different color. Let's use blue. I've got y equals x plus 2. In order to graph that, the idea is the same. It's already in slope-intercept form, so I'm going to start at my intercept at 2. So my y-axis, put a point at 2. And then my slope, I don't see a number there, but we know that means the coefficient is 1. So my slope is 1 over 1. So starting there at 2, at my y-intercept, I'm going to go up 1 over 1. Up 1 over 1. And the reason I'm putting so many points on my graph is because, remember, we said we're looking for the intersection point. It's real easy when you've got a lot of points to see what I just did there. I put a point on top of one of those points from the black line. That lets me know right here, that's where those lines are intersecting. I can put a couple more points if I want, but I've got what I'm looking for. So the question is asking, what is the solution point? If I'm using that definition of solution points, that solution points for systems are the points that lie on both lines. I see here there's only one point that lies on both of those lines. It's that point right there. Now, if I'm answering the question, what is the solution point? I need to label that point. Remember, we're going to label it with an x-coordinate and a y-coordinate. This point right here on our x-axis, this point is at the number 3. On our y-axis, this point is at the number 5. So we can say the solution point to the system is the point 3, 5. So instead of what we were doing yesterday where I would give you a point like this and ask, is it a solution point, yes or no, we're actually starting to find them ourselves. And this is going to be one of our methods. One way you can solve these systems is by doing what we did here, by graphing both of those lines, finding where they intersect, and that intersection point is your solution point. So this is my first example. I've got one more we're going to look at. If I wanted to find the solution point for our system right here, what is the first thing we would want to do? You may be saying something like graph this first line. If that's what you're saying, I love it. Looking at this line here, we would graph it similar to what we were doing before. It's in slope-intercept form. So I'm starting with my intercept at 3. My slope is -3/2. So if I'm comparing that to rise over run, it's negative, which means I'm going down. I'm going down 3 and over 2. Down 3 and over 2. Down 3 over 2. I can do the opposite. Instead of down 3 over 2, I can go up 3 backwards 2, up 3 backwards 2, and that's all that can fit on the graph. I'll go ahead and draw my line. That's pretty good. What would you want to do next? Well, next we would want to do the same thing. We would want to graph this equation. Hopefully you're seeing this equation does not look like the other ones we've graphed so far. This equation is not in slope-intercept form. I know that because slope-intercept form starts y equals. It's the form y equals mx plus b. This equation here is not in that form. So our first step before we graph it is I need to change it into slope-intercept form. I need to solve for y to make it look like this one. So in this equation, y is right here. In order to solve for y, I'm going to start off by getting rid of my 4x here. I'm going to do that by adding 4x to both sides. When I do that, that leaves me with 2y equals, I can write -8 plus 4x, and that's perfect. I'm going to go ahead and put that x first, because we know in slope-intercept form the x comes first and the y-intercept comes second. So instead of writing -8 plus 4x, I'm going to write 4x minus 8. And then our last step, if I want y by itself, I want to divide by 2 on both sides. When I do that, it leaves me with y equals. Notice over here I'm dividing everything by 2, dividing my 4x by 2 to get 2x. And then that minus 8 divided by 2 gives me minus 4. And like that, I've got my second equation that I can graph now. Now I can see that the y-intercept is negative 4. And then my slope is 2, so I want to go up 2 over 1. Up 2 over 1, what do you know? The lines are intersecting. I can do it a couple more times, but I've got what I'm looking for at this point. Is there anything else I need to do? Hopefully you're saying, I got to answer the question still. This graph is not the answer to the question, what is the solution point? It's just the method we're using to find the answer. But if I'm asking you, what is the solution point? Well, you got to tell me what that point is. Our answer should look like a point with an x and a y coordinate. So for this graph, they're intersecting here. That point is on 2 on our x-axis. And then the y-coordinate, this point here is at 0 on our y-axis. We're not having to go up or down at all. So we've got the point 2, 0 is our solution point. Now before we finish up with this question here, I want to relate this back to what we did yesterday. If you've had me for a while, you know I do not miss an opportunity to show you how you can check something in math. And I love systems of equations, by the way, for so many reasons. But one of the reasons I love them for you all, especially right now when you're at home, is there's a way you can check your answer for every single system. If I think this is my solution point for this system of equations, how could I check to make sure it's our solution point? Well, we can check by doing what we did yesterday. I'm going to give myself some room for this. Yesterday, remember, the questions were something like what I'm asking now. The questions were me giving you a point and asking you, is it a solution point? That's kind of where we're at now. I think this is the solution point, but I want to check my answer. Well, if this is the solution point, one thing that should be true is it should, on that graph, be the point that's on both lines. But the other thing that should be true is this point should satisfy both of these equations. That means I can check my answer by substituting our point into both of these equations, like we did yesterday, and making sure that it satisfies both of those equations. So let's do that. I'm going to take my first equation, which is y equals negative 3/2 x plus 3. Go ahead, pause the video, check it yourself. Make sure if you substitute this into the equation, it gives you something true. Well, when I go to check, 2 is going to be my x, 0 is going to be my y. So it'll say 0 equals negative 3/2 times x. X is 2, but I'm going to write it as 2 over 1 to help me with the multiplying fraction. And then plus our 3. We get 0 equals negative 3 times 2 is negative 6. 2 times 1 is 2. And then plus 3. Here we get negative 6 divided by 2 is negative 3. And negative 3 plus 3 is in fact 0. For the second equation, when I go to check, I want to check my solution point in the original equation. Remember, this is the equation we ended up changing to be in slope-intercept form. But I want to use the original equation because let's say I did make a mistake. That mistake could have happened when I was changing this equation. So I'm always going to go back to that original system. So I've got this as my point. I'm going to check it in this equation here. Same idea. Go ahead and pause the video and try it yourself. Okay. So if I check this point here, it's going to be negative 4 times 2 plus 2 times 0 equals negative 8. Negative 4 times 2 is negative 8. 2 times 0, did you say it was 0? Not 2. And then we get negative 8 plus 0. Negative 8 is in fact negative 8, so it checks out there. That's what we're looking for. So for any of these, in this entire unit, just not in today's lesson, but this entire unit, if there's ever a system problem like this, where you are solving the system, you get an answer, and you want to check to see if your answer is correct, for example, maybe on a test on this stuff, you could always do that by doing what we just did here. If your answer is correct, it should satisfy both of the equations. I'm going to erase all of this, and I've got a couple questions for you to try. The first two are a little different. They should be quicker, though. And then I'll have one similar to what we just did here. For the first one says find the coordinates of the solution point below. Well, here it's already been graphed for you, so all we have to do is label the solution point. That solution point is right here where those lines intersect, which is at the point 1, -1. The second one says draw a system that has a solution point at 2, 1. So it's kind of like the opposite of what we're doing. I know you can't, unless you have graph paper at home, I know you can't draw this yourself, but you could go ahead and describe for me what you would do to draw that system, or if you have like a piece of paper, you could draw it for yourself as well. Please know that for this question here, there are many, many possible answers. I'm going to start mine off just by showing where I want the solution point to be. The solution point should be at 2, 1. So 2 on our x-axis, 1 on our y-axis. This is where my solution point should be. If I want to draw a system that has a solution point here, there are so many possible correct answers, because all you need to do is draw 2 lines intersecting at this point. Just like here, there's 2 lines intersecting at our solution point. The idea is the same. It does not have to be the 2 lines I draw. I'm going to draw one here, and let's do this one right here. Something like that would be good. You could draw lines going whichever direction you want. It's got to be 2 lines intersecting right there at that point, and you can draw them however your heart desires. The last practice question for this part of the notes is going to be most similar to what we've been doing. The question says, graph each equation, find the solution to the system of linear equations. So here is your system. Again, I know not everyone's going to have graph paper at home. Do the best you can. There's some things you can still do for this problem. All right. Well, the one thing you could do, even if you don't have graph paper, is I can't graph both these lines until they're both in slope-intercept form. This equation here is not in slope-intercept form. So I need to do that. When I go to change it in slope-intercept form, I'm trying to get y by itself. So I need to get rid of this 3x by subtracting. That gives me y equals -3x plus 2, and it's already in slope-intercept form. So I've got this line here I want to graph and this line here. Even if you don't have a graph like I do here, you could always make yourself like a little drawing. I wouldn't write all the numbers out, but you could just do something like this where you can plot some points to find the solution. I'll give you a preview of where we're going. One of the reasons we have 3 different ways to solve systems is because graphing is a really great way if you have graph paper, but obviously not everyone at home watching this video right now has graph paper. I'm a math teacher and I don't even have graph paper at home. So that's why we've got so many different ways we're going to learn how to solve these, is because sometimes one way might not be the best way. If you don't have graph paper at home, this way we're learning right now might not be the best way. So that's why we've got some of our lessons coming up are going to be other ways you could solve these systems. But I do have graph paper. So we're going to go ahead and solve this one by graphing. We've got y equals 3x minus 4. So I'm going to start at my minus 4, go up 3 over 1, up 3 over 1. Like I've been saying, I'm going to give myself a lot of different points for this first one just so I can really clearly see where the second line intersects. Our second line is -3x plus 2, so I'll start at 2. I'll go down 3 over 1 for my slope, since it's -3. So going down 3 over 1, let me draw my line here first. But when I go to graph the second one, I'm going down 3 over 1. I see where it intersects. Can do it one more point, but I'm going to go ahead and draw our lines. Ooh, I don't know if that one was really straight. But it doesn't matter if it's straight because I see my solution point. It's this point right here. If I want to label that point, that is 1 on our x-axis, and that point is at -1 on our y-axis. So we get the solution point is 1, -1. There's one more thing I could do with this problem. Do you know what I could do? Are you at home saying, ah, yes, she wants us to check it? Then you would be right. You're a mind reader. Yes, we could check our answer for this. Because the numbers are pretty nice, this might be one that if you wanted to try checking it in your head, you could. I've got the point 1, -1. If I were to put 1 for x, put a 1 right here, 3 times, put a little multiplication sign. 3 times 1 is 3. 3 minus 4 would give me y. 3 minus 4 is -1, and y is -1. We could do the same thing down here. 3 times my x, which is 1. 3 times 1 is 3. And then our y is -1. So 3 times 1 minus 1. Well, 3 times 1 is 3. Minus 1 gives me 2. That's what I'm looking for. Sometimes checking your head like that is too much. You could always write it down too. I'm just showing you lots of different options. But by checking that, we know our answer is correct. There is one last part to these notes, and it has to do with something I said yesterday and something I said at the very beginning of this lesson. When we were talking about solutions to systems of equations yesterday and at the start of this lesson, I said, well, a system of equations is 2 equations. That's 2 lines. 2 lines intersect at one point. And I lied just a little bit there. If you were thinking, as you heard me say that, well, not always, you'd be correct. Think about it. Most of the times we have 2 lines, they are intersecting at one point. But that's not going to happen every single time. On occasion, you could have 2 lines that look like this, or 2 lines that look like this. It looks like one line, but imagine if you graphed the first line, and then when you graphed the second line, it's in the exact same spot. So the last part of these notes are talking about types of solutions. The majority of the time, when you go to solve by graphing, 2 lines are going to be 2 different lines that intersect in one point. This is going to be what a lot of our systems look like. And for a system like this system has one solution. Just like we said yesterday, just like we said at the beginning of this lesson, it has one solution. That one solution point is that one intersection point. And if I asked you what is the solution, you would answer by telling me what that solution point is. So for this one here, the solution point is -2 on x and 1 on our y-axis. However, that is not always going to be the case. I'm actually going to start, I think, with this last one here. Looking at this system, I've got 2 lines, but how could I describe these 2 lines? Well, these 2 lines are going the same direction. They are parallel lines. Parallel lines are lines that go the same direction. Parallel lines are lines that never intersect. Because they're going the same direction, they're never going to cross paths. Well, that's a problem. We said our solution point is a point that lies on both of the lines. And yesterday, the student in the room said, oh, it's the intersection point, which is perfect. But if I have 2 lines that never intersect, where's the point on both lines? Well, there isn't one. And if I pick any point, this point here is on one line, but not the other. This point here is on one line, but not the other. This point here, one line, but not the other. There's no point that lies on both of the lines. So something like this, if you have a system with parallel lines never intersect. There's no point that's on both lines. That means there is no solution. There's no solution point. So we say this system has no solution. So this is one other option for something that can happen with a system. Now that middle one, that last option here, remember we said, picture you've got two equations. Maybe the equations even look different, but you've got those two equations, and when you go to graph them, they ended up being in the same spot. Well, let's go back to that definition of solution points again. We've been saying a solution point is a point that lies on both lines. Well, if the two lines are in the same spot, any point I pick on one line is going to be on the other line because they're on top of each other. All of these points I'm marking lie on both of the lines because those two lines are the same. They're in the same place. Well, here it's like the opposite problem over there. I can't label a point because there's a ton of them. There's a ton of points on both lines. Do you know what we're going to say for this one? We got the word yesterday. There are a ton of points on both lines. So here we say there are infinitely many solutions. Infinitely many solutions. For a system like this, the two equations might look different, but when you change them into slope-intercept form, you're going to get the same line because they're the same line. And because they're the same line, they're in the same place. And because there are so many points that are on both of those lines, we say there are infinitely many solutions. I can't just name one. These are the three types of solutions you can have for systems. So keeping that in mind, we're going to look at two more problems. Hopefully you forgive me for lying to you just a little bit. Like I said, just a little bit. But now that you know everything there is to know, you know all three types of solutions, I've got two more problems for us now. So looking here, we've got graph the system of equations. The question I'm asking is a little different this time. I'm not asking what is the solution point. I'm asking how many solutions does the system have. For this first one, let's go ahead and graph. If I graph this first equation here, it looks like it's missing some stuff. Don't forget, we've always got slope-intercept form we can go back to. If that y-intercept is missing, it means it was 0. So my first point I'm going to put here on our origin. That's the 0 on our y-axis. And then my slope, if I don't see a number there, that means the slope is 1. So you can think of it as 1 over 1. And I can go up 1 over 1. And I'll do a bunch of those points. Go ahead, draw my line. We're going to come down here for the second one. Here, my y-intercept is -4. So I'll put my first point here. My slope, again, is 1 over 1. So starting from this point here, I'll go up 1 over 1. And I'm getting a bunch of points here. Now that we've got the graph, what's my answer to the question going to be? The question is, how many solutions does this system have? This system here, we're going to say has no solution. If I asked you why it has no solution, you could say because they're parallel lines. You could say because the lines never intersect. You could say because in order to be a solution point, the point needs to be on both lines, and there's no point that's on both of the lines. Lots of different ways you could justify that. What about this second one here? See if you can figure it out. Okay. For this second one here, in order to figure out what the graphs are going to look like, I have to change both of them into slope-intercept form. This first one here, the first thing I would want to do is bring that 2x to the other side. I do that by subtracting 2x. When I do that, I get 4y equals -2x plus 12. I can then divide by 4. That gives me y equals -2 divided by 4. Be careful. 4 divided by 2 is 2, but 2 divided by 4 is a fraction. That is -2/4. You could simplify that by dividing by 2, and it gives you -1/2. So I've got -1/2 x. Over here, I'm going to do it again. 12 divided by 4. This time it's not a fraction. 12 divided by 4 is 3. So I've got y equals -1/2 x plus 3. If I wanted to graph that, I'm going to start here at my 3. My slope is -1/2, negative, so I'm going down. I'm going down 1 over 3. And I can't do that anymore, but I could go up 1, backwards 3, and get, whoo, that's a little wiggly. Get that line right there. I'm going to do the same thing for my second equation. So this one, I'll put it up here. We've got x plus 2y equals 6. I'm going to subtract x from both sides. That gives me 2y equals -x plus 6. I'm going to divide both sides by 2. And we get y equals, this is similar to what happened before, negative, that's -1 over 2. Be careful. You cannot divide 1 by 2. That's a fraction. It's -1/2. So I get -1/2 x. And then 6 divided by 2 gives me a 3. So I've got y equals -1/2 x plus 3. At this point, you actually don't even need a graph to figure it out, because look, I got the same lines. If I go to graph this, I'm starting here at 3, and I'm going down 1 over 2. It's going to end up being the same spot. So I get the same line. Because the lines are the same, how many solution points? Here my answer would be there are infinitely many solutions. Infinitely many solutions, infinitely many solution points, something like that. Again, if I asked you to explain why, you know I love asking you to explain why, what could we say? Well, there's infinitely many solutions because the lines are the same. There's infinitely many solutions because there's infinitely many points that are on both lines. You could say the lines are the same, so whatever point's on one line is on the other line. Lots of different ways you could explain that. Hopefully you're feeling pretty good about this lesson. One of the things I do want to mention is this lesson relies a lot on your ability to graph, which is something we learned back in Algebra 1A. If you're still feeling not as confident as we want you to be with graphing, please reach out to me or Denise and we can give you some extra practice just on graphing one line. Once you get really good at graphing one line, this is like the same idea, you're just graphing two. But if you need some extra support, help, whatever it may be on graphing lines in general, please let us know, because practicing that skill is automatically going to help you with everything we're doing here. Once again, if you're taking ASFAB right now, I see you outside. Hello. I hope you are not stressing too much about the test, but I wish you the best of luck. And I will be very happy to have you back all in class again tomorrow. But if you're at home, have a wonderful day. I'll see you all later. Bye.